Hi, Stu Schwartz from MasterMathMentor.com. This is video BC18. The topic is Geometric and pSeries. It covers the BC manual, pages 96 and 97. This video features two special series, the geometric and the pSeries. A geometric series is in the form of summation n equals 0 to infinity of ar to the n, which is a plus ar squared plus ar cubed plus dot 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 plus ar to the n plus dot dot dot, and a is not equal to 0. The constant r is called the ratio. The geometric series test is based upon the absolute value of the ratio. If this value, the absolute value of r, is greater than or equal to 1, the series will diverge. But if the absolute value of r is less than 1, then the series will converge. And not only that, we can actually determine its sum. It will be a over 1 minus r. Following our 9 infinite series, use the geometric test to determine whether each series is convergent or divergent, and if it is convergent, find its sum. Number 1 reads summation n equals 0 to infinity of 2/3 to the n, which is 1 plus 2/3 plus 4/9 plus 8/27 plus dot dot dot. Following our general rule, we may want to use the nth term test first. The limit as n approaches infinity of 2/3 to the n is 0, but all that means is that the series could converge. We're going to find that the nth term test will in general be useless unless it's clear that it diverges. So we realize that this is a geometric series with r being 2/3, which is less than 1, so this is convergent. To find the sum, s is equal to 1 over 1 minus 2/3, and to clear the complex fraction, we multiply by 3 over 3, getting 3 over 3 minus 2, which is 3. 2 reads summation n equals 0 to infinity of 3/2 to the n. This is 1 plus 3/2 plus 9/4 plus 27/8 plus dot dot dot. Since r is equal to 3/2, which is greater than 1, this is a divergent series. Note that this could have also been done with the nth term test because the limit as n approaches infinity of 3/2 raised to the n is infinity, and therefore this is divergent. 3 reads summation n equals 1 to infinity of 5 times 1/4 to the n power. This is 5/4 plus 5/16 plus 5/64 plus 5 over 256. Since r is equal to 1/4, which is less than 1, this is convergent. To find the sum, there's a little trick here because this summation goes from 1 to infinity, not 0 to infinity, and our formula is for 0 to infinity. So we will calculate the sum from 0 to infinity and then subtract the first term, which is 5 times 1/4 to the 0 power. So our sum is 5 over 1 minus 1/4 minus 5. To deal with the complex fraction, we will multiply by 4 over 4 and get 20 over 4 minus 1, which is 20 over 3 minus 5, which is 5/3. Here are 6 more series, and you are to determine whether they are convergent or divergent, and if convergent, find their sum. In number 4, we have summation n equals 0 to infinity of 8 times 3/4 to the n. This is 8 plus 6 plus 9/2 plus 27/8. And this is a geometric series with r being 3/4, which is less than 1, so it does converge. And therefore the sum is 8 over 1 minus 3/4. Multiplying by 4 over 4, we get 32 over 4 minus 3, which is 32. Number 5 is similar. Summation n equals 0 to infinity of 8 times negative 3/4 to the n. This gives 8 minus 6 plus 9/2 minus 27/8 plus dot dot dot. This is called an alternating series. We will study them in depth later. The absolute value of r is equal to 3/4, which is less than 1, so it too converges. And therefore the sum is equal to 8 over 1 minus negative 3/4, which is 8 over 1 plus 3/4. And multiplying by 4 over 4, we get 32 over 4 plus 3, or 32 over 7. Number 6 reads 1/10, summation n equals 0 to infinity of 1.1 to the n. This is 1/10 plus 11 over 100 plus 121 over 1,000 plus 1,331 over 10,000 plus dot dot dot. R in this case is 1.1, which is greater than 1, so it diverges. Even though it looks like we are adding small fractions, this will diverge. In number 7, we are given the series 4 plus 2 plus 1 plus 1/2 plus dot dot dot. Whenever you're given the actual terms and you suspect that that is a geometric series, it is best to divide by the first term, factoring it out. And when we do so, we get 4 times the quantity 1 plus 1/2 plus 1/4 plus 1/8. And we realize that this is a geometric series for summation n equals 0 to infinity of 1/2 to the n power. Since r is equal to 1/2, which is less than 1, it converges. And therefore the sum is 4 over 1 minus 1/2, multiplying by 2 over 2, we get 8 over 2 minus 1, which is 8. 8 is 4 minus 2 plus 1 minus 1/2 plus dot dot dot. And this is almost exactly like number 7. We again factor out the 4 and get 1 minus 1/2 plus 1/4 minus an 8 plus dot dot dot, getting 4 summation n equals 0 to infinity of negative 1/2 to the n. The absolute value of r is equal to 1/2, and therefore it converges. And therefore our sum is equal to 4 over 1 minus negative 1/2, which is 4 over 1 plus 1/2, multiplying by 2 over 2, we get 8 over 2 plus 1, which is 3. So the sum of this series is 8/3. In number 9, we have 10 minus 4 plus 1.6 minus 0.64. Again, we factor out the 10 and we get 1 minus 2/5 plus 4/25 minus 8 over 125 plus dot dot dot. And we realize that this is a geometric series, 10 summation n equals 0 to infinity of negative 2/5 to the n. The absolute value of our r is 2/5, which is less than 1, and therefore this is convergent. So the sum is 10 over 1 minus negative 2/5, which is 1 plus 2/5, and multiplying by 5 over 5, we get 50 over 5 plus 2, or 50 over 7. Our third special form is called a pSeries. A pSeries is in the form of summation n equals 1 to infinity of 1 over n to the p. And this is 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p plus dot dot dot. A pSeries will converge if p is greater than 1, but it will diverge if p is less than or equal to 1. In number 10, we have 1 plus 1/4 plus 1/9 plus 1/16 plus dot dot dot. We can write this as 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. And this is summation n equals 1 to infinity of 1 over n squared. This is a p-series with p equals 2, and it is convergent. Here is a graph of the sequence in blue and the series in red. It does appear that the series is converging to some limit, but the pSeries test does not tell you what that limit is. It just tells you that it does exist. Number 11 reads 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4 plus dot dot dot. This is 1 over 1 to the 1/2 power plus 1 over 2 to the 1/2 power plus 1 over 3 to the 1/2 power dot dot dot. And that is summation n equals 1 to infinity of 1 over n to the 1/2 power. This too is a p-series, but p in this case is 1/2, and therefore this is divergent. Here is a graph of the sequence in blue and the series in red. Notice that the sequence is converging to 0, but the series appears that it is going up forever. It is very easy to get confused with the geometric and p-series. The geometric form is summation n equals 0 to infinity of ar to the n. It does not necessarily have to start at 0. It could start at any constant. But in the r is constant and the power is changing in a geometric series. For the p-series, it is in summation n equals 1 to infinity of 1 over n to the p. Again, n does not have to start at 1. It can start anywhere. But for the p-series, n is changing and the power stays constant. 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot 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 is the infinite series summation n equals 1 to infinity of 1 over n. By our rules, this is a divergent p-series because p is equal to 1. This is an important series and it is called the harmonic series. We again graph our sequence points in blue and our series points in red. It is obvious that our sequence points is converging to 0, but our series points appears to be going up forever. That is not proof, but it appears that they are not leveling off to some limit. A general harmonic series is in the form of summation n equals 1 to infinity of c over an plus b. This will diverge. In music, strings of the same material, diameter, and tension, whose lengths form a harmonic series, will produce harmonic, which is pleasing to the ear, tones. So if you encountered 2 over 1 plus 2 over 4 plus 2 over 7 plus 2 over 10, and you realize that this was equal to summation n equals 1 to infinity of 2 over 3n minus 2, applying the nth term test will just tell you that the series could converge, and you need another test. However, if you realize that this is in the form of a harmonic series, c over an plus b, where c is 2, a is 3, and b is -2, this is the harmonic series and will always diverge. The points as shown suggest that, as the blue points are the sequence and the red points are the series, and again it appears that it is getting larger and does not show any sort of limit. The harmonic series is a fascinating series. Diverging means that its sum will become larger than any positive number m in a given number of terms, even though that sum is becoming larger at a snail's pace. We use the spreadsheet to find out how many terms would be needed for the sum to be greater than m. Look at the table. When m is 2, it only takes 4 terms, 1 plus a half plus a third plus a fourth, for our sum to be greater than 2. But it takes 31 terms for it to be greater than 4, 227 terms to be greater than 6, 1,674 terms to be greater than 8, and 12,367 terms to be greater than 10. When m gets to be numbers like 100 or 1,000, the number of terms will be astronomical. But again, we're playing with infinity, and infinity goes on forever, so we have as much time as needed for that sum to be greater than any value of m. Still, it seems counterintuitive that the harmonic series diverges. So here's a proof. We look at summation n equals 1 to infinity of 1 over n, and we will write it with some parentheses. 1 over 1 plus 1 over 2 plus quantity 1/3 plus a fourth plus quantity 1/5 plus 1/6 plus 1/7 plus 1/8 plus dot dot dot. And you should agree that this is greater than 1 plus a half plus the quantity 1/4 plus 1/4 plus the quantity 1/8 plus 1/8 plus 1/8 plus 1/8. So our harmonic series must be greater than 1 plus a half plus a half plus a half plus dot dot dot. And since summation n equals 1 to infinity of 1 over n is greater than the divergent 1 plus a half plus a half plus a half plus dot dot dot, summation n equals 1 to infinity of 1 over n is divergent as well. Suppose we stack identical books of length 1 so that the top book overhangs the book below it by 1/2, which overhangs the book below it by 1/4, which overhangs the book below by 1/6, etc. This structure is called the Leaning Tower of Lear, and it will just barely balance. The length of the overhang is 1/2 summation k equals 1 to n of 1 over k, where n is the number of books. And this is the harmonic series. And theoretically, it will balance with an infinite number of books. It will take 31 books for the overhang to be 2 books long, 227 books for the overhang to be 3 books long, and 272 million books for the overhang to be 10 books long. Try it with a deck of cards. If you ask most students to take one divergent series and then subtract another divergent series and determine whether the result is convergent or divergent, most would say that the answer would be divergent. After all, each of them are infinite. But we have to be careful in making a generalization. For instance, look at the summation n equals 1 to infinity of 3 over n minus summation n equals 1 to infinity of 2 over n. The first series in blue is 3 plus 3/2 plus 3 over 3 plus 3 over 4 plus dot dot dot. And we know that to be a harmonic series. 2 over n is also harmonic. 2 plus 2 over 2 plus 2/3 plus 2 to the 4th, etc. If we do the subtraction, we get 1 plus 1/2 plus 1/3 plus 1/4 plus dot dot dot, which is summation n equals 1 to infinity of 1 over n. And that makes sense. 3 over n minus 2 over n is simply 1 over n. So in this case, A divergent series minus a divergent series also is a divergent series. But let's look at summation n equals 1 to infinity of 1 over n minus summation n equals 1 to infinity of 1 over n plus 2. They are both harmonic. The first series is 1 plus a half plus a third plus a fourth plus a fifth, and the second series is 1/3 plus 1/4 plus 1/5 plus 1/6. Both are harmonic and both diverge. However, if we reorder the terms, we get 1 plus a half plus a third minus a third plus a fourth minus a fourth plus a fifth minus a fifth plus ... and our answer is 1.5, as this is a telescoping series. So in this case, a divergent series minus a divergent series becomes a convergent series. So be very careful about making generalizations with series. Do not trust your instincts. Many times they will be wrong.